Hi, my name is Chad Austin. I'm a technical director at IMVU. And today we're going to talk about Embind, which is a library we've developed to be able to connect C++ and JavaScript as it was compiled by, or sorry, C++ was compiled into JavaScript. Who here was at Alone's talk on Mscriptin yesterday? So a fair percentage of the room. So we're going to do a brief overview of Mscriptin, but this talk is not by itself about Mscriptin. We're going to talk about what IMVU is and why we ended up selecting Mscriptin as sort of a key component of our technology strategy, and also why we ended up building Embind. We're going to cover an overview of Embind's features, what you can do with it, and the reason that I'm here actually at this conference is C++ 11 really is what made Embind possible. There's several tricks that we took advantage of that use things like type traits and variadic templates and whatever. And the tricks that we're going to look at specifically are around code size and syntax. As a point of order, at the end I'll try to leave 10 minutes for questions, but in the sort of the first 45 minutes or so of the presentation, I'm just going to go as fast as I can. Okay, so what is IMVU? We are a social platform where users can sign up, get an account, dress up an avatar, and then go around chat rooms and stuff and meet people from all around the world. We also have games and activities that you can do with people. So we're sort of like a social network, but a little bit more lightweight than something like Second Life. We've been around for about 10 years, and to our knowledge, we are the largest virtual goods catalog on the internet. All the content in the world is created by our customers. So why did we end up choosing Mscriptin as our sort of next generation technology platform? This is our current offering, which is a downloadable application for Windows and Mac. There's a Mac build as well. Windows and Mac are great, but the issue is there are more platforms out there, right? There's mobile. We might want to run some of our code on the back end. We might want to run our code in a browser without any download at all. So we were thinking, how do you have a single code base that you deploy across all of these platforms? The answer sounds like it'd be C++, right? C++ runs everywhere, but then the question is, what about the web? So in 2011, I did some research into Mscriptin and found that it's actually quite suitable for this. And so Mscriptin compiles C++ into JavaScript. And with the Asm Js project, Mscriptin compiled code is actually about half the speed of native, which is well within the ballpark of acceptable performance, at least for our purposes. So that's definitely okay. And that, to be honest, was surprising. Even back in 2011, the performance was acceptable for our perspective. The big advantage is that there's no download required, and you don't need a plugin, right? Because customers are a little bit afraid of downloading software for security reasons and whatever. So it's nice if you can just click a link and go to a web page and see some content. Also, when you port your application to Mscriptin, you sort of automatically port it to a whole bunch of platforms. You get Windows and Mac and Linux for free. We never would have considered porting our application to Linux because there just wasn't the market for it. But our Mscriptin builds run out of the box, and that's actually convenient for our engineers, some of whom run Linux. You also get a handful of mobile devices, an increasing number of mobile devices, and tablets. So the conclusion that we came to is that C++ is the high-performance language if you want to run on all platforms, including the web. Here's a screenshot of our application in development. It's the same product offering as our download for Windows and Mac, except it runs straight in a browser. You might see this is Firefox here. All the content's rendered with WebGL. The chatting is being done with WebSockets. The UI is built with HTML5, CSS. And I'm not exactly sure why there's a snowman in the river, but that's what's going on in this room. So let's briefly talk about what Asm Js is, just so you have a rough sense. Asm Js is a subset of JavaScript where the operations in the JavaScript correspond almost directly to machine instructions. That is, you can compile the browser can compile the JavaScript into really fast executable code. The memory space in Asm JS is represented by an array buffer. So JavaScript allocates a block of memory, and then it assigns 8 typed array views that alias into that buffer. This is just like the normal C heap, right? There's a 8-bit signed number view into the heap. There's a 32-bit unsigned view into the heap, and a 64-bit float view into the heap, and so on. And they all alias each other, which corresponds to normal C and C++ rules. For more details here, Alone Zakai has a bunch of resources, and the Mscriptin.org website does as well. I gave a presentation at GDC last year, which is, you can look at the slides at engineering.imvu.com, that sort of covers the overview of like what Mscriptin is, how it works, and how we use it. And here's a little example. Imagine you have a C++ function. This is just a trivial example. You pass in a pointer to a number, and the function increments it. Once you run this through the compiler, what you get is a JavaScript function that takes the pointer as an argument. And that pointer in JavaScript could be anything, right? It could be a floating point number or a string or whatever. So if you look at that first line, p equals p bitwise or 0, that tells JavaScript, I want unsigned 32-bit semantics for this value, right? P bitwise ORed with 0 becomes a 32-bit unsigned number. Then we load from the heap. That's what this heap U32 is. We load from the heap, we add 1, we convert back to an unsigned 32-bit number, and we store it back out in the heap. And that's approximately what Asm JS code looks like. Of course, functions get more complicated as you compile more code. So Mscriptin can compile C++ into JavaScript, but that's just half of the picture, right? Because if you can run code on a platform and run it, that's useful, but it's not useful unless you can actually access the platform. So you need some APIs that you can call. Mscriptin provides implementations of a fair number of POSIX APIs. So you can typically take some Linux program and build it, and it'll run. I've seen a demo of WebKit actually running in the browser using Mscriptin. And there are also some hand-rolled APIs to access browser functionality that you wouldn't normally have on another platform, like set timeout, which lets you run code in the future in the browser event loop, or you can eval JavaScript with an Mscriptin API. So let's talk a little bit about what this might look like if I wanted to use one of these functions. In JavaScript, if I wanted to run some code a second down the line, I would call set timeout, and I'd pass my function, and then I would say 1,000 milliseconds. So in 1 second, the browser is going to run this function. In Mscriptin, I can do the same thing with the Mscriptin async call function. And I pass in a little capture list lambda, which turns into a function pointer, and whatever my opaque argument value is, and then 1,000 milliseconds. It's the exact same thing. This approach is great for things that are sort of common. The problem is browsers have thousands of APIs, right? And they're growing. The set of APIs that's being added to the browser platform is actually pretty large. So ideally, you'd want some way just to talk straight to those APIs and not have to have convenient wrappers built for you. In addition to that use case of having C++ code that wants to talk to the browser using just directly calling APIs, you might want to have the other direction where, let's say you're building some kind of web application in JavaScript, some website, and you say, I want to do some blowfish encryption. What's a good library for that? And let's say the only mature library you can find is written in C++. You'd love to be able to just run that C++ code within your JavaScript application. So Embind sets out to solve these two use cases. Sometimes I want to call JavaScript from C++, and sometimes I want to take existing C++ code and expose it to JavaScript so that people can use it. So what is Embind? It's a binding API between C++ and JavaScript. It's bidirectional. At any point, either language can call each other. The syntax was very heavily inspired by Boost Python. The Embind project itself is included within the Mscriptin project. So any check-ins go straight into the Mscriptin GitHub, and Alone's very good at getting those merged in a timely manner. And in addition, it's, like I said, it uses very heavy use of C++11, to the point that I didn't really know C++11 before I started this project, and then by the end, my head was pretty much melted. So Boost Python is something that I've used a lot, probably in the last 10 or 15 years. Every single C++ project I've developed has used Boost Python in some way or another. Overall, I think it's great, but it's got a few things that are a little bit annoying, mostly around performance. So I'll never forget talking to a PlayStation 2 developer at the Game Developers Conference. This was, I don't know, maybe 5 or 6 years ago, and they were trying to use they tried to use Boost Python at one point on the PlayStation 2, and they said that it cost an entire millisecond to call from Python into C++, into one of their APIs. That's 1/16 of your frame budget. So that was just simply not acceptable. We actually see this at IMVU in the desktop client too, where you might go through 16 to 20 stack frames before you even get into C++ from Python. So, that's one thing I certainly didn't want Embind to have, especially because on Mscriptin, you're paying a little bit of a penalty for running in the web in performance. Code size is also a huge problem, and that's a problem for two reasons. One is your DLLs that you ship to your customer with Boost Python end up being enormous. Another is the compiles take forever. And then I have a little taste nit, which is that in Boost Python, there's a lot of bindings that are sort of generated automatically for you and a lot of implicit behavior, and I prefer to make everything explicit in my APIs. So. With Embind, I sort of set out with different goals. I wanted, well, this is shared, I guess. In terms of the bindings, I want them written in C++. I don't want people to have to do a custom build step for their bindings and have like Swig or some of those tools. I mean, they work fine, but it's just a little bit annoying to have another tool in your tool chain that you have to run. I wanted the bindings to use JavaScript terminology when appropriate, because when you're building a C++ API, you're building an API for C++ consumers, right? So that's the mindset you should be in. When you're using Embind, you're actually building a JavaScript API that happens to be implemented in C++. And so it's important to think about it that way. You're not letting JavaScript have access to your, C++ world. You're giving JavaScript a good API, and that just happens to be C++. Performance is important, so I wanted runtime overhead to be as small as possible. This requires runtime code generation. You have to be able to, the bindings layer rather, synthesizes, whenever you bind a function, it synthesizes sort of the optimal call path from JavaScript to C++ and vice versa. And it does this at runtime, so the compiler doesn't have to do any extra work there. That all happens at the binding layer. The implementation, for my own sanity, is pretty short. I think it's just 3 header files, and that's so there's a hope that other people will contribute to the project and so on. I think there actually have been 3 or 4 different contributions to it from non-MView people, which is pretty cool. So let's talk about binding C++ to JavaScript, that is, letting JavaScript call into C++ code. Here's an example of what some bindings look like. Inscription Bindings just says, run some code at global scope, right? It's just that block of code is basically a function that runs before main. The function call registers a function pointer to JavaScript, and you have to give it a name, because JavaScript needs to create a function of that name so you can call it, right? So JavaScript doesn't know what the name of the function pointer is. You have to give it one. Same for classes. Name a class, give it a constructor. It has 2 arguments, an int and a string, and we'll also bind a member function into JavaScript. This actually goes, C becomes there's no classes in JavaScript, there's a prototype. Who here is familiar with JavaScript object semantics? Wow, surprising number of people. Yeah, they're not a direct map for C++ or really anything else. So this method becomes a property of C's prototype object under the scenes. But it kind of, from the JavaScript side, instance of still works and method calls still work. Embind supports classes and member functions and statics and all sort of the normal things. It also supports JavaScript Properties, which is when you access a property, it calls a function. When you set a property, it can call a C++ function, and so on. And there are two ownership models today. One is raw pointers, where the JavaScript has sort of like a raw pointer to some data in the Mscriptin heap and then has to clean it up. There's also a shared pointer model where you can actually share some objects across C++ and JavaScript if you want. Embind also supports enumerations. Both styles work fine. There's constants, and JavaScript can extend C++ classes. So if you have a C++ class with virtual functions or some kind of interface or something, it's possible to extend that and implement it in JavaScript if you want. And we do support overloading, but we only support overloading by the argument count. We don't do the ridiculous like type inference system that Boost Python does to try to figure out which one to call, because not partially for performance, but also because like semantically there's not that many numeric types in JavaScript, right? There's just the numbers. So it would be weird to try to figure out which overload matches best for a given number value. So we just punt on the issue and say you only overload an argument count. Here's how to bind a property. Let's say I have a little character struct. How much of that is cut off? Actually, none of that. Good. Let's say I have a little character struct, and I've got a health property on it, and a setter and a getter. This is all pretty vanilla. I'm going to bind the class character, give it a constructor with no arguments. That is basically the default constructor. And bind the property and pass the getter and the setter in. Whenever that property is read from JavaScript, it's going to call the C++ getHealth function, and then same for whenever it's mutated, it will call the setHealth function. Embind sets all that stuff up for you, so you don't have to think about it too much. Here's an example of how you bind enumerations. Pretty straightforward. The main thing is you just have to give everything a name, because JavaScript needs names for things. Constants. The constants can be of whatever type. You can even do custom type constants, and that'll work fine. There is something that's really important to know, which is that JavaScript's a garbage collected language, but it gives you no insight into when that garbage collector runs. There are no weak pointers, there are no GC callbacks, no finalizers. There's occasionally someone will pipe up on the ECMAScript discuss mailing list and say, like, we need weak pointers or finalizers, and then long, contentious argument happens and nothing changes. So I'm not sure if we're going to ever get this, but hopefully we do. In the meantime, that means you have to do manual memory management on your C++ objects from JavaScript. You might be doing that already, because if you're writing a complicated web application, you probably need to unregister your jQuery event handlers and stuff at the appropriate times. But it's just something to think about. So let's look at what that might look like. Imagine I have a two-dimensional point and a little function that can make a point. Pretty simple example. I'm going to bind that point class to JavaScript, and then I'm going to bind the function. So when I call it from JavaScript, p equals make point 1020, p.x is 10. That's good. That's what you'd expect. It means everything got initialized correctly and you're reading the values out of memory and stuff. But what is p? P is just this like weird generic object thing. It's actually, in this case, it's an Embind instance handle. P is a JavaScript object that holds a reference to a pointer that is pointing into the Mscriptin heap, right? There's a point which has two ints floating around in the Mscriptin typed array somewhere, and this P object that I've got from JavaScript is pointing to there. So I actually have to deallocate it, and that's really unfortunate for simple things like this. If you have a two-dimensional point, like, why do I have to deallocate that? To that end, Embind provides a value type construct where you can denote that, like, this type is a value type. I want by-value conversions between the languages because it's just a two-dimensional point. I don't care about instance lifetime management. So we support two modes of that you can do that to JavaScript objects or to JavaScript arrays. For example, for point, you might have an object. This is just a generic JavaScript object, x:10, y:20. And then for arrays, you might say, well, two-dimensional points are simple enough that I can just do x, y as my JavaScript representation of a point. To bind something like that, you use value object or value array. Value means value type, and then object means to a JavaScript object. Give it a name, give it the fields it needs, and then once I call the new binding from JavaScript, what I get back is actually just a JavaScript object. I don't need to delete it. It's just in the garbage collected heap. So we've talked a lot about taking some C++ code and exposing it to JavaScript. So let's go the other direction for a little bit. There's a type in Embind called Mscriptin val, and val represents an arbitrary JavaScript value. So maybe it's a Boolean, maybe it's an object, maybe it's a null, whatever. So in JavaScript, if I wanted to get the current time, I would call date.now. That returns the number of milliseconds since the epoch. In C++, if I want to do the same thing, then I can use val for that. So here at the bottom, where you see val global date, that does a lookup of the date object in JavaScript, right? Because the date object is a global that's provided by the language runtime. So I could say val : global date, and then I can call a method on it. .call now. The template argument here is the return value that I want. So this is the exact same thing that I wrote before, except you can just conveniently do it from C++. I might actually want to, if I had a whole bunch of date code going on, I might even want to just save off a copy of val global date and then just call it capital date from C++, and then just use it whenever I needed to. Here's a little bit more complicated of an example. So let's actually write a C++ program, and in main, we're going to use the web audio API. Here we can see val global audio context. That looks up the global audio context constructor, and then we're going to call new on it. So this new underscore is the same as just saying new in JavaScript. Then we're going to call the create oscillator method, set the type to triangle, set the frequency, and then connect it up in the media graph to the destination, and then play start. And I think the 0 means like start now or whatever. So after running this, you'll hear a triangle wave coming out of your speakers. And this is all C++ where you're just interacting with the JavaScript API. Interacting with JavaScript from C++ generally happens in the implementations of your Leaf modules. So you might have a file system module or a network module, and you're like, on iOS I do this, on Android I do this. Well, with Mscriptin you'll say, okay, on Mscriptin I'm going to talk to this particular web API. And this is sort of a good use case for this side of Embind. Okay, so that's pretty much all of the Embind features. So let's talk a little bit about how it's implemented and what's going on under the scenes. Every C++ type is assigned a type ID, and a type ID is just a number that identifies that type, and it's unique. Type IDs get names associated with them. When you bind some type information, you have to say what it is. And also, every C++ type gets a wire type. So wire types are the marshalling layer between the languages. Whenever you want to pass a value from C++ to JavaScript, first it goes to a wire type, and then it goes to JavaScript, and then JavaScript constructs a JavaScript value from that wire type. Here's an example of some common wire types. Anything primitive, or like the C++ numeric types, their wire type is exactly the same as the primitive type, right? If you want to pass an int between JavaScript and C++, it's the same. You don't have to do any translation. However, strings, JavaScript doesn't understand what a standard string is. It doesn't know how the memory is laid out. So it has to be transferred in some way that the Embind layer in JavaScript can sort of figure out what the string data is. We do that with just an anonymous little prefix encoding. I think we write the size in the first 4 bytes and then the rest of the characters. Same for WString. And then on the JavaScript side, out comes just a normal string object. For any given class, though, for like almost everything in your program, the wire type is just a pointer to an instance of that class. And then JavaScript gets the Embind handle and can manipulate it. So let's dig in a little bit and see what happens when I write a binding. Let's say I have a function, take two floats, add them together, and spit out the result. This function, when I bind it, what I'm giving it is 2 bits of information, the name for JavaScript and the function pointer. But Embind needs 3 bits of information. It needs to know the signature, right? It needs to know the arguments and the return type so that it can hook up the appropriate marshalling code. So underneath, this is actually the function that's getting called. Here's the name you gave it, and then the last argument is the function pointer you gave it. Right? That's the 2 bits of information you gave. The rest of this is all signature. It's the number of arguments to the function, it's the type IDs of the return value and the arguments, and the Asm Js signature string. The Asm Js signature string is necessary because in Asm Js, function pointers are typed. Right? They're not just like indices into an array of instructions, right? They're actual, there's tables. The Asm Js spec talks about all this stuff. You don't need to know all the details, but there's basically tables for each type. And then a function pointer is an index into that table. So when we pass a function pointer to JavaScript, we also need to tell JavaScript, this is the table it's going to be in, so you know where to find it. So if I bind a function, the actual code that's generated looks something like this. Register function, here's the string I passed, 3 arguments because one of them is the return value. Here's the list of arg types, float, float, float. Here's the signature string, FFF, all for float. Here's an invoker function, and here's the function pointer I gave it. These 4 middle parameters are just signature information. And then you don't need to look at this too much, but basically the Embind register function call is called from C++, but it's implemented in JavaScript. So JavaScript takes all this information you're giving it, and then it crafts that optimized code path so that calls can be quick between JavaScript and C++. So now we're starting to look at the implementation. Let's talk a little bit about some C++ 11 techniques. So there's 2 main categories here. The first one is code size, and I'll talk about why code size is so important in a minute. And then the second category is some syntax hacks that make things a little bit easier to use. So why is code size important with Mscriptin? In a native application, to load an executable, all the OS does is memory map your exe or whatever into memory, and then just begin executing instructions. It's as simple as that, which means it's really fast. It doesn't actually matter whether your executable is a gigabyte or 4 megabytes or 100 kilobytes because it's just memory mapped. It's not a big deal. And stuff is just paged in on demand. In JavaScript, however, that's not how it works. The browser has to download the JavaScript using the customer's network connection, probably cache it in some kind of local cache. Then it has to parse it into a parse tree from bytes. Then it has to code gen in some way, and depending on how you target your executable, you might get the, in Firefox you might get the Odin Monkey ahead of time compiler, but in Chrome you're going to get the V8, just-in-time compiler. So your customer basically has to do all the register allocation on their own computer before they can even run your program. And they don't just do it like on small parts of it. They might try to code gen a chunk of it before they run your program. So even dead code hurts you in the Mscriptin target. So you want to try to emphasize keeping your code size down. So to that end, we set out to solve a couple problems, which is, let's go back to this function binding. We're trying to bind add to, and we've given it the function pointer, and then there's all this signature information. Signatures, they're known at compile time. They're type-based, so the compiler knows all this. They're constant, and they're also shared across a whole bunch of different functions, right? Plus takes 2 floats and returns a float. Multiplication takes 2 floats and returns a float. Raising a float to the power of a float is also a float, right? So the signature is the same for all 3 of those. And in my head, that was like, I wonder if I can use constexpr for this. I don't exactly know what constexpr does, but let's see. So we're going to talk about these Asm Js function table signature strings. So if I have a signature, let's say I have a function that returns void and then takes 3 arguments, float, int, and a character pointer. The signature string for that is going to be VFII, F for float, and then int I, but then also it turns out everything else is an I as well, pointers and stuff like that, right? Everything else is integral. So what I wanted here was to take some type information, right? I have this signature at compile time. How do I generate a compile time string literal? The first thing I need to be able to do is turn a type into a character, which I knew how to do in C++11. I can make a struct called signature code, and I can put a static constexpr method on it, right? And it just returns a, I probably don't even need a method here. I probably could have done that with a constexpr static property on this object. But now I can take a type and turn it into a character. So everything is an I unless it's a void, in which case the character is V. Otherwise, if it's a float, it's an F. If it's a double, the character is D. But okay, so character, now how do I get to a string literal? This function here takes a function pointer. The function, the pointer value itself was never actually used, just the template type information, right? So this here is a function pointer argument on getSignature, and the template arguments are the return type and the argument types. Static constexpr character array, where the first entry in the array is the signature code of the return type, followed by the signature codes of all the argument types, followed by the terminating 0. And then I can return that array from the function. It turns out that in Clang, in Mscriptin at least, this function, when you call it, generates absolutely 0 code at runtime. The result is a constant that is a pointer into your static data segment, basically, where it's put your array data. And that turned out to be a pretty big win for code size, because previously I had a little template program that was generating all this data on the stack for every call, which was completely wasteful. So now let's maybe see if we can do some similar optimizations to the Arg Types Array. This Arg Types Array, these are just type IDs like I talked about. Type ID is just an integer or a void pointer that identifies a type, and it's used as an index into the type registry, just so Embind knows what you're talking about when you talk about a type. Originally, I just used C++ type ID, the RTTI mechanism. The type ID definition was just a pointer to a const type info record. This turned out to be a pretty severe problem for code size because type ID pulls in a whole pile of information that you probably don't actually need, like the mangled name, for example, especially on some of the longer templates. It gets really, really long. And I think there was also some records for like traversing hierarchies and stuff, but we didn't need any of it. We just need some kind of identifier. So yeah, type ID wasn't that good. In addition, we don't even need the name because we're already providing a name for every type when we write the bindings. We're providing a good human name that the author wrote, right? Not something that the compiler generated that's really hard to read. And moreover, those names are only used for error messages. Like, whoops, you called a function with the wrong type. Or there actually is one case where you might want the compiler-generated name, which is if I call a function where I forgot to actually write bindings for the return type, then you'd want Embind to say, hey, you called this function, but you forgot to bind the return type, and this is what its return type was, using the type ID name. But that's only useful if you forgot to write bindings, which only happens when you're developing your application. So once you're done developing all your bindings, then you can just turn that off and set Mscriptin has unbound type names to 0. Because all Embind needs, like I said, just a number and a name for every type. Now the lookup of a type should be constexpr. And there is one case where we still need RTTI, and that's for polymorphic pointers. Embind, if you return like an interface pointer, Embind sometimes will say, hey, what's your actual type? So that I can see if I understand that. And if I do, then I'm going to give you some rich information about it, right? The actual rich bindings. So because we need to support type ID as well, the light type information also has to inhabit the same namespace as type ID. Otherwise, we might have namespace collisions. We can't just like start an integer at 0 and increment, and because that could conflict with type ID pointers. Who knows? So the change here was to change type ID to a const void pointer and implement and get light type ID to say if the type that I'm trying to get the type ID from is polymorphic, then use RTTI. Otherwise, use the light mechanism. So what is that light mechanism? There's a light type ID struct that, when instantiated, allocates a byte in the static data segment and uses the address of that byte as the type ID. You know this is going to be unique with in the same namespace as type ID, and thus won't conflict. And I'm not exactly sure why the linkage works here. It feels like it shouldn't, because I just put this part in a header, and I didn't get any like duplicate symbol definitions or anything. So maybe this is okay. Great, this is okay. Got a nod from the audience. And this was an enormous code size savings. It actually shaved 175 kilobytes off of our minified JavaScript, which was a big deal for us. And the only thing that you're paying is a single 0 byte in the static data segment, which probably gzips down to 0 and doesn't even take that long to parse in the browser. And then finally, once we've got that mechanism to be able to look up a type ID, we can generate compile time arrays of those and put those in the static data segment too. So here's, if I have a whole bunch of types, then I can call get type IDs, which is a variadic template function, and place that in the static data segment. Some of those might have come from the static data segment. I have no idea how the compiler's like sort of finalizing all these numbers in the end, but it works out. So the final code generated for a function binding looks like this. It's Embind register function, and then a whole pile of numbers. And those numbers are just indices into various tables, because table-driven code is often the smallest code, right? That's how you try to pack things into as small as possible. Okay, so those are the code size optimizations. I'm just going to talk about this this one syntax hack, and we're going to skip the second one so we can go to questions after that. So sometimes you want to bind overloads, right? The POW function is a great example from the standard library. There's 3 overloads, I think, float, double, and long double. And if I just naively try to bind it, it doesn't know which POW you're talking about, so this is actually a compile time error. So you can use a C-style cast to pick which signature you want, and that's what that looks like. And it works, and this is what Boost Python does, and it's sort of okay. But I really don't like C-style casts. One is because they're kind of ugly. You have to, put that pointer there, and I don't always remember function pointer syntax. They're also a little bit dangerous, because if POW ever got refactored so that it wasn't an overload anymore, all your casts are just like, okay, that's fine, I'll just cast this to this other thing, and the compile won't fail for you, but then when you try to call it at runtime, God knows what happens, right? In Embind's case, it would probably end up using a function from a different function table or something like that, and that would be awful. So I wanted something where I could just say, I want this particular signature of this function. And I don't want, if I'm wrong, then give me a compile time error. So what's the implementation of select overload? Note that I'm passing in a function type. Select overload, given a function type, all it does is it takes a function pointer and then returns it. So it doesn't actually do any work. It just forces the compiler to pick which one you're talking about. So that was useful, and that was a pretty big win, but it turns out that most bindings are classes and not actually functions. So what if I had something like this, where I've got, this is sort of an old convention that people, I don't know if they still use it or not, where if you want a getter and a setter, you just give it the same name, and if it takes no arguments, it's a getter, and otherwise it's a setter. What if I wanted to bind those to JavaScript? You can do that with C-style casting, where you say .method prop, and then I want to sort of do a pointer to member function cast here, C-style cast, so that Embind knows which one you're talking about. I find that hideous for two reasons. One, it duplicates the class name. So in this case, has property, has property, has property, has property. And especially if your class is really long, it's just like, it's all over the place. And also because the same reasons as before. I don't know if casting pointers to members works the same way. I don't know if it's as dangerous as functions, but I just find it gross. And I wanted the same syntax where I don't care what has, I don't care what the class part, I just want to specify which signature I want. So can I make select overload do the same thing and not duplicate the class name? Well, it turns out I can. I can overload select overload to take pointers to members. And the member is a function, right? So this first template argument on select overload, that's the one you specify. That's the function you want. Class type is inferred. You already know. You're passing in a pointer to a particular member on a particular class. You don't need to say what class that is. It knows. So then the argument is a pointer to a member, and then returns that straight up. No code generated, just helps you figure out which one you want. And I can remember this a whole lot easier than I can remember pointer to member syntax. So that's why I like it. Okay, we're going to skip this one because the implementation is pretty gnarly, and because we don't have time, I want to make sure that you guys have a chance to ask questions. But afterwards, after the conference, feel free to look at the slides whenever they go up on the website or whatever. It turns out it's not that trivial to deduce the signature of a captureless lambda, even though captureless lambdas can be converted into function pointers. So they can be converted to a function pointer. Function pointers have types, but doing that automatically required like walls of template cook. And anyway, not going to cover that right now. Overall, I think C++ has a bright future on the web. There are a whole bunch of libraries that are now available because you can just find it online. If it works well and people have been using it, compile it with Mscriptin, it's going to run fast, and then use it from JavaScript. You can also call JavaScript from your C++ applications that you're porting to the web. And the performance here, from our perspective, is fine. Like, it's just not an issue. I measured recently, it came up in some questions. Someone was like, what is the overhead of doing all these calls? And I measured it 200 nanoseconds on my home machine, which is like well within the realm of I just don't care. There actually are more optimizations that we could do if we wanted to. If somebody had a use case where, for whatever reason, they had to cross the language barrier a whole bunch, there's still room to improve here. We just haven't been motivated to do that yet. The emphasis was on small generated code size. I think we've succeeded, mostly just by measuring and profiling and measuring, and then finding some clever trick that we can do to optimize it. And without C++ 11, I'm not sure that I would have had the energy to build Embind. C++ 11 is so nice. Variadic templates are, like, especially for this stuff where you're talking about signatures and stuff, it's so much better than the Boost Python, like Boost parameter macro expansion stuff. That gets hairy fast. So I hope you learned a few things today. Thank you for listening, and now I think we have some time for questions.
Do you have a feeling as the overhead of calling JavaScript function from C++? I'm interested in knowing whether inline caches still work properly or not.
The question was, how is the performance of calling JavaScript from C++? There are actually two mechanisms for calling JavaScript from C++. One is the dynamic way that I showed, where you sort of act like, you just have these generic JavaScript objects and you're calling through. Those tend to not be as good because you're looking up function names by like C string literal pointers, right? So then that string literal pointer has to then be converted to a JavaScript string, and then the function has to be dynamically looked up. Browsers don't like that as much. There's another way which works better, which is where if you have an interface, like for example, our WebGL interface. We have a interface called GL, and it's got a whole bunch of WebGL methods on it. And then there's an implementation of that interface that's glued to a JavaScript object. That implementation is faster. There's a couple ways that we optimize that we don't optimize the other. Last I looked, there was one optimization I still wanted to do on that side of things, but it's really not an issue. Like WebGL call overhead is going to dwarf that. And also calling between the Asm Js, like on Firefox at least, calling between the Asm Js OdinMonkey JavaScript and the non-Asm Js OdinMonkey JavaScript, there's a penalty you have to pay there where you marshal stack frames and stuff. I don't know exactly how it works. And so you probably just don't want to call that much between the languages. It's better to build up arrays of knowledge and then pass that knowledge across. Like I've thought about building a streaming WebGL implementation where the WebGL commands are actually marshaled on the C++ side into a buffer, and then they just get shipped over in one blob, and that turns into JavaScript calls. Does that answer your question? Yeah. Great.
How do you actually debug this?
How do you debug this stuff? That's a good question. You can just use your browser's debugger, where Chrome or Firefox. We do a special build of our engine that we call like northstar.debug.js or something like that. And it's got function names that correspond roughly to the C++ function names, and the variable names mostly match up. And it's all, we had closure run across it, but only in the small simplification mode, so that it's still fairly easy to read. Like some of the redundant variables are removed. So we just use the browser debugger. We also have a build of our application that runs in Visual Studio. So if you're doing stuff that doesn't talk about bindings or the JavaScript side, you can just debug that in whatever. Yep.
So if I get this right, you have JavaScript that's normal JavaScript talking
Mm-hmm.
to a JavaScript that compiles C++, and then you take all of this and you try to do things to it with an optimizing compiler, just like it was C++ in the first place, kind of. So you said that C++ has bright future on the web, so how do you think this should look like? Because what we have right now seems to be a mess.
Yeah, so the comment was we have JavaScript and C++ compiled JavaScript, and they're all sort of mashed together into one thing and then shipping that out. It is kind of a mess, and actually, Alone knows this. I used to rant about, JavaScript can't possibly be the right thing here. Like, I was a big fan of Portable Native Client and Google's efforts there, and I still am, but for various technical reasons, it actually doesn't work for our use case. So it is what we've got. It's a really weird platform, but it works really well in practice. And the main thing is there aren't too many other scenarios where you're shipping 3 megabytes of JavaScript to your customer. And so browsers aren't necessarily that good at handling that today. But there's some open bugs on Chromium and stuff. As the stuff gets more common, browsers are going to want to do it quickly. Does that help answer your? Okay, great. You first.
You mentioned Asm Js. That's one's for Firefox. So what for you guys do Chrome? How's that work?
Yeah, so Asm Js itself runs on any browser just fine. It's just a subset of JavaScript.
Okay, but you'll get performance increases, right?
You actually do get some performance increases on.
Not the same level as Firefox.
Right, so Firefox takes Asm Js to the next level. Other browsers will find patterns and optimize things, and Chrome, tends to like that style of code because all the variables have the same type all the time. They'll never, the types never actually change. So Chrome will always hit its caches on, I know what this function is because it always gets these types, and but in Firefox you actually get substantial performance improvements because these instructions. I forgot to mention that increment slide way back there. I don't know if I can make it back there in time. That slide where I had the increment with the number, that line of JavaScript probably gets compiled down to 1 machine instruction. Maybe 2 if there's a bounds check there or not.
Firefox.
In Firefox, yeah.
Right now.
Yep. And probably Chrome actually, dynamically. I would suspect V8 would do that too.
Almost certainly, because the types don't change, it'll compile it to the same machine code.
Mm-hmm.
On small micro benchmarks, the performance between Chrome and Firefox is essentially the same. It's just on larger code bases, there can be some variability.
That's what we've seen too. Yeah, in Chrome, performance-wise, because there's so much code, it's like heuristics about when to cache functions and how many functions to cache at a time and how big a function or how many times a function has to get called before it gets cached. It really penalizes large code bases, whereas the Firefox Asm Js implementation does an ahead of time compile on everything and then never recompiles anything, which is optimal for predictability. Does that help?
Oh, yeah.
Great.
Is it possible to include Windows APIs in the implementation? Let's say we are compiling in Visual Studio, like Windows APIs.
Is it possible to have Windows APIs?
Yeah, inside the C++ code base.
As long as they can be backed by JavaScript somehow, because the browser is the only thing you've got access to, unless you were running. Oh, that's a good question. So are you talking about on Windows RT where you can do the?
Like Windows APIs, the example, you want to access the file system or something related. Let's say you want to call the print API or something.
Got it.
You want to get the from driver list of printers available in local Windows machine.
So the web browser has no access to any of those APIs. So if you're living on the web platform, you can't do that. But if you wanted to Mscriptin compile something and run it in like Windows scripting host or something, I don't know, maybe you could do that. I probably wouldn't recommend it because I don't know why you would do that.
That's the reason I was asking, like, Internet Explorer and all, you used to have all these plugins and activants.
Mhm.
Those things is possible to port to this platform and use it.
You can only do it if the platform if you're running in the browser, you get browser APIs. If you're running in Node.js, you can have Node.js APIs and so on. So it depends on which JavaScript world you want to live in. Most people, if you're porting to JavaScript, you probably want to run in the browser. But the browser's, for security reasons, is pretty sandboxed. So, okay, yep.
So is this a smooth experience? So I'm going to take my library, fairly sizable, and just throw it in this and it's just going to work?
In my experience, the biggest factor in terms of smoothness of porting is how dependent you are on APIs, like depending on which APIs you're using. If you have like a big math library, it'll be trivial. You could probably do it in half a day, port it to the web. If you have something where you're doing, say, threads, which aren't, you depend on threads, the web doesn't provide that today. So you're going to struggle a little bit, unless you can do a single-threaded build or something. Trying to think if Alone probably has a bunch of examples in his head.
I mean, the threads really is the best example.
Yeah. So it depends.
That's a question to Mscriptin, not particularly.
Mm-hmm. Right. Yep.
So Asm Js will recompile everything. This is important from the latency perspective for the user. Is this pre-compilation take a long time for the download?
Yeah, so the question is, this pre-compilation of Asm Js in Firefox specifically, how does it affect latency, like the customer experience when loading the page? I think, so Firefox, if you do script defer or something like that, correct me if I'm wrong, it will actually do the compilation on another thread, and I think it does multi-core compilation, right? Right, so your script might take a little bit to load, but it shouldn't hang the browser or anything. So it's not a big deal. But code size is still important, and especially if you're going to target other browsers like Chrome that don't do all this stuff.
It's probably less than 1/10 of the time to download. So we load like 16 megabytes of the file, it takes, depending on the server connection, let's say 30 seconds, then it takes 1 second.
Yeah, in our experience too, that we take about 1.5 seconds to parse and compile the JavaScript. So it's just like it's a slight problem, but it's not a big deal. Any other questions? Sure.
Just didn't quite get where you get the third-party library, you try to compile it and you get those operations. Where do these go? They are not part of the original library, so.
Oh, I see. Yeah, so when you write bindings, that's just C++ code. So let's say this function is provided by the library here. when you do the bindings, what you would do probably is write a file. If your library is called foo, you maybe have a file called foobindings.cpp. You put all your bindings in there, so they're isolated, and then you just build that into the whole library. Right, right. You might have to do that anyway because you're using Mscriptin's compiler and not GCC or Clang or whatever. So you probably have to do something to the build system of the library. But yeah, you just link in the bindings file and spell all the bindings you want out, and now you've got a JavaScript API for your C++ library. Great. Any other questions?
Is there a tool? I missed the Inscription presentation. Is there a tool that will generate these for you? Or
the question is there a tool that will generate these for you? There is not yet. There theoretically could be. There certainly are for other systems like Boost Python and whatnot. And I have a slight aversion to those tools because I think that when you're exposing an API, you should be precise about what you're exposing so that you're not exposing all kinds of internal classes. I've worked on projects where we've done automatic bindings, and I've got some horror stories, and I've sort of had that. So we certainly could write a tool like that, especially now that we have awesome parsers and stuff in the LLVM project. It probably wouldn't be hard. So I think we're out of time. If you have any further questions, then feel free to come up. Thank you.